Hello everyone, welcome to IIT Gate classes. This is lecture 8 on compiler design. In this lecture, we are going to start operator precedence parser. Okay, so let me revise. Okay, so in the previous class, we have completed top-down parsers. Okay, top-down parsers we have already completed. And in this class, we are going to start our first bottom-up parser, that is operator precedence parser. Okay. So what exactly is operator precedence parser? Well, so before studying this, we have to study what are operator grammars. Okay. After studying operator grammars, we will be able to understand what exactly is this parser. Okay. So what are operator grammar? A grammar is said to be operator grammar, okay, if it follows two conditions. Okay, so let me write those conditions. Or and rather, we should say precisely, operator grammar will be a CFG. Okay, a CFG is operator grammar. OG means operator grammar if it follows two conditions. Okay, what are those conditions? The first condition is no two known terminals can be present side by side. No two known terminals can be present side by side in RHS. Okay, in RHS, no two known terminals can be present side by side. And the second is there should be no null productions. Okay, there should be no null production. So only we have two rules which we have to keep in mind. No null productions. Okay. The first rule is in RHS, no two non-terminals can be present side by side. And second is there should be no null productions. Let me give you some example. You will get more clarity. Okay. Please note it down. I will jump to the next slide now. Yes. So now I will show you some examples. Okay. So for example, if I am having E implies E plus E star E or ID. Is it operator grammar? Yes. Why? Because we have two non-terminals in RHS and they are not side by side. There is a terminal between them. Here also two non-terminals and here we have a terminal between them. Here we have only terminal, no problem. If I say S goes to AS or B, yes, this is also operator grammar because in RHS no two non-terminals are present side by side. That's it. But you just have to remember one thing. No two non-terminals should be present side by side and there should be no null productions. Okay, if I say AS or null, no, it is not operator grammar because we have null production here. Okay, now if I say S goes to SAS or B, okay, and A goes to BSB or B. Is it operator grammar? No, because see, we have two non-terminals present side by side. So this is not operator grammar. Okay. Now, if I say like this, S goes to ASA or B, yeah, this is operator grammar because no two non-terminals are present side by side. That's it. So I have given lots and lots of examples. By now you have got clarity about what exactly is operator grammar. Okay, and let me give you just one more example. SBSBS BSBA. Yeah, this is also operator grammar because see, no two non-terminals are present side by side. These two non-terminal and here we have a terminal between them. Here we have two non-terminal and here we have terminal between. So no problem at all. This is operator grammar. Okay. So I hope I have made the point clear to all of you. Please note down all these examples and I will jump to the next slide now. Okay. Yes. So to study the operator precedence parser, okay, we should know operator precedence table. Okay, same case. See, I have already told you parsers have four things, or you can say four parts. Okay, let me revise. What are those four parts? The very first part is table. Second is algorithm. Third is stack, and fourth is buffer. Okay, so buffer will store the string. In the buffer, we have dollar at the end. Here we will store the string. We have a stack with dollar at the bottom. Okay, and we have a table like this, and we have an algorithm. Okay, so same scenario here. Algorithm will decide what to do and so on. So table, buffer, table, stack, and algorithm. So four parts. Okay, so four parts in every parser. So obviously operator precedence parser is also a type of parser only. So this will be having these four parts. So let me discuss one by one. So the first part is table. Okay, so how to construct the table? Let me show you some example. Okay, please note it down. I will jump to the next slide. Yeah. So let me show you some example. Okay, so we have a grammar like this: E goes to E plus E star E, and ID. If you try to remember, this is ambiguous grammar. I have told you many times why this is ambiguous and so on. You can watch my previous compiler design lectures. And in TOC also I have discussed that this is ambiguous grammar. Okay. Now for this ambiguous grammar, I am going to construct the table. I have already told you many times, operator precedence parser is a special type of parser. OPP, operator precedence parser, is special type of parser. Why we are calling it as special type? Special type of parser because it can parse few but not all ambiguous grammar. That is the main advantage of operator precedence parser. Okay, so it is a special type of parser because it can parse few but not all ambiguous grammars. Okay, so but none of the parser, I have already told you this is an exception. That's why I'm calling it as a special type of parser. It is an exception because no parser can parse ambiguous grammar. Why no parser can parse ambiguous grammar? Because if grammar is ambiguous, then we can have two or more parse tree for a string, and which parse tree is correct, which parse tree is wrong, we do not know. Okay, so parser will get confused at that moment. Hence, no parser can parse ambiguous grammars, but operator precedence parse is an exception which can parse few but not all ambiguous grammar. So for this ambiguous grammar, I'm going to construct operator precedence parser. Okay, operator precedence parser I'm going to construct for this grammar. So let me start. Okay, let me start, and I'm constructing table first. Okay, so first thing is table. How to construct the table? Okay, for the table, actually, this table is known as operator precedence table. Operator precedence table. Okay, so how we will construct it? We will see the operators here. Okay, plus star and ID. Operator means terminals only. You can consider operators as terminal. Okay, so terminal symbols. All the terminals will become operator. So plus star and ID, and we will consider one extra terminal, that is dollar. Okay, so dollar which represent the end of the string. Okay, so see this now. This is the dollar. Dollar at the end of the string, and dollar in the first symbol in the stack, and so on. So we will consider dollar also as operator. Okay. So how many operators are there or terminals are there? We have three terminals here. So we will construct table like this. So I will write ID plus star dollar. Here also ID plus star dollar. Okay. Yeah. So now we will make, okay, we will make this table. So how we will make? So first rule is ID and ID cannot be matched. So here we will apply dash. Similarly, dollar and dollar cannot be matched. So here we will apply dash. ID has the highest precedence. So this will be the case. Here also we have ID. So ID is having more precedence. Similarly, in case dollar is having least precedence. So here we will show like this, and here we will show like this. Okay. So what are the basic points? ID and ID can't be matched. Similarly, dollar and dollar can't be matched. ID has highest precedence. Okay, and dollar has least precedence. Okay, please note down these points carefully. Now comes this plus and plus. How you will match plus and plus? Okay, so imagine this is your left plus, this is your right plus. Okay, so plus is left associative, na? So I will write like this. Similarly, plus and star. Who is having more precedence? Star is having more precedence than plus. Then star will be like this. If you are not able to follow, don't worry, please. When I will show you some examples, you will get more clarity. Okay, now this star and this plus. So star is having more precedence. Star and star. So consider this star as the left star and star is left associative. So I will put symbol like this. Okay, this is the way to construct the table. Now, see, right now I will not be able to explain much about this table. Once I will jump to the algorithm part of the operator precedence parser, you will get more clarity. Okay, and how I have constructed this table, please note down carefully. I have not seen this grammar. I have just applied the rule of mathematics. That means plus is left associative, star is left associative, star is having more precedence than plus, and so on. That's how I have filled the table. Okay, so please try to remember this fact. Whenever grammar is ambiguous, this table should be constructed according to rules of mathematics. Okay, if grammar is unambiguous, then according to that grammar, we will fill this table. Okay, please try to follow these steps. Okay, please note it down carefully. I will jump to the next slide and I will write down these points because these are very, very important points. Okay, yeah, so I'm jumping to next slide. So the first important points. The first important point is, if grammar is ambiguous, then make the table according to rules of mathematics. Okay. Second, if grammar is unambiguous, then make table according to grammar. How you will make the table according to grammar? Don't worry about it. We will study it in the after few slides. Okay, don't worry about it. Okay, third important point is, see how many cells in the table. Okay, so number of terminals are 3. We have added one extra terminal, that is dollar. So 3 plus 1 4 and 4 multiplied by 4. These are the total cells. So number of cells will be what? T plus 1 whole square. Okay, T plus 1 whole square are number of cells in the table. Okay, and what is the basic disadvantage, or you can say, of this table? See, in real life, let us suppose we have C language compiler and we have lots and lots of operators. So assuming we have 100 operators, then number of cells in this table will be how many? Let us suppose 99. Just for the sake of convenience, I am assuming 99 operators. So 99 plus 100, 100 square, that is 10,000. 10,000 cells will be there in this table. So table will become very, very large. Okay, that is the main disadvantage. Okay, so too much space is required. Disadvantage is too much space is required. What is the disadvantage? Disadvantage is too much space is required to store the table. Okay, so these are few important points which we should remember. Now let us study this part. If grammar is unambiguous, then make table according to grammar. So how you will construct it? I will show you this thing now. Okay, please note it down carefully. I will jump to the next slide now. Yes, I'm jumping now. Okay, so for example, if grammar is E implies E star T or T implies T plus F or F goes to G arrow F or G goes to ID. If this is your grammar, okay, and I think you all remember from my previous classes of compiler design, when we were studying this ambiguity rules, I have told you how to solve these questions. Star is having more precedence or plus is having more precedence. So level decide the precedence. Okay, and recursion decide the associativity. So star is what? Left recursion, na? So left associative. Plus is what? Left associative. Arrow is what? Arrow is right associative because right recursion. And who is having highest precedence? Arrow is having more precedence than plus. Okay, and plus is having more precedence than star. So lower the level, more is the precedence, and so on. I have already told you all these things. So if you are not able to follow, please watch my disambiguity rules lecture. You will got the clarity. Okay, and now I will try to make the table according to this only. Okay, so let me write the operators. Okay, so what are the operators here? So id plus star, arrow, and dollar. Similarly here id plus star, arrow, dollar. Arrow is power operator. Okay, I think you already know. 2 arrow 3, that is nothing but 2 power 3, that is 8. Okay, so this is power. Okay, and here we have dollar, not G. Sorry for that. This is dollar. Okay, let me draw the table first. Okay, then we will jump to the main part. Okay, yeah. So as I have already told you, ID and ID cannot be compared. Dollar and dollar cannot be compared. ID has highest precedence. So blindly you will keep like this. Here also ID is having more precedence. Dollar is having least precedence. And here also dollar. Yeah. So now plus and plus. So left associative. See here, plus is left associative because of left recursion, like this. Plus and star. Now please do not say according to mathematics star is having more precedence and so on. See here, star is at higher level, plus is at lower level. So plus is having more precedence than star. Okay. And what about star and arrow? Arrow is having more precedence because it is at the lower level. Arrow is having more precedence. Then star and plus. See, star is at higher level, plus is at lower level. So plus is having more precedence. Star and star, see here. Star is left associative. So I will keep like this. Star and arrow, arrow is having more precedence. Arrow and plus, arrow is having more precedence. Arrow and star, arrow is having more precedence. Okay, see carefully the level. Okay, arrow and arrow. See, arrow is right recursion, na? So arrow is right associative. So like this. Okay, imagine this is as right part, this is right, and this is left. Yeah, so we have constructed the table. So by now you have got more clarity about how you are going to construct the table. Okay, so now let me show you the algorithm part. Now you will get more clarity. Okay, so let me jump to the previous slide. A table we have already constructed. Okay, so for this grammar table we have already constructed, and now I'm going to show you how this parser is going to work. Okay, so I will say id plus id star id, and at the end we have dollar. Okay, so we are assuming this is our string id plus id star id. Okay, and dollar is at the end. Okay, now how we will construct the parser? Okay, so we will have stack. Okay, let me show you stack here. We have a stack with dollar at the bottom. Okay, look ahead pointer is pointing to the first symbol, that is id. Okay, and see, we will say dollar and id are compared. Okay, so imagine this is your stack part. Okay, imagine this is your stack part. This is your stack, and this is your buffer part. Okay, so if what we will say, uh, if buffer, see here in buffer we have read this id, and in the stack we have read the dollar. So in the stack we have read the dollar, and in the buffer we have read the id. So ID is having more precedence than dollar na. So more precedence means push. Okay, more precedence push. It's just like your data structure and algorithm. You have studied na prefix, postfix conversion and so on, evaluating postfix expression and so on. It is just like that only. Okay, so more precedence means push. So I will push ID onto the stack, and whenever something is pushed, look ahead will move to the next symbol. Now plus and ID. In the stack we have read this ID, and in the buffer we have read this plus. So less precedence means pop. Okay, more precedence means push, and less precedence means pop. Less precedence means pop. So I will pop this ID. Okay, and what exactly popping means? Popping means reduction. That means ID is reduced to E like this. You can imagine like this. Okay, now ID has been removed, so plus and dollar are compared. Plus is having more precedence than dollar, so plus will be pushed on to the stack. Since it is pushed on to the stack, look ahead will move one symbol to the right. Okay, so now ID and plus are compared. ID is having more precedence than plus, so ID will be pushed on to the stack, and look ahead will pointer will point to the next symbol. Now star and ID are compared. See here carefully. Star and ID are compared. ID is having more precedence than star. So obviously ID will be popped off. Okay. ID will be popped off. Popped off means what? It will be reduced to E. Okay. Now star and plus are compared. See here carefully. Star and plus are compared. So what does this mean? Star is having more precedence than plus now. So star will be pushed on to the stack. Since we have pushed it onto the stack, we will move to the next symbol, that is ID. Now ID and star are compared. ID is having more precedence, so it will be pushed onto the stack. ID will be pushed onto the stack, and look ahead will move one symbol to the right. Okay. Now I will say dollar. Now it's obvious now, because dollar is having least precedence, so all of them will be popped off one by one. So I will say dollar and ID are matched. ID is having more precedence than dollar now, so it will be popped off. Popped off means what? ID is reduced to E. It is popped off. Now dollar and star are compared. Star is having more precedence, so it will be popped off. Popped off means what? See here, star has been popped off, so E star E is changed to E. That means what? This means E star E is changed to E. Now next is dollar and plus. Dollar and plus are compared. So obviously plus is having more precedence, so plus will be popped off. Popped off means what? See here, E plus E is changed to E. So here also we are having E plus E is changed to E. Okay. Now see, nothing is left. So dollar and dollar are compared. Okay, and we will say string is accepted. Okay, so finally we have got this. So if we try to see carefully how we have constructed the parse tree, see here, E goes to E plus E, and E goes to E star E, E goes to ID, ID and ID. This is the exact parse tree which we want. Okay, because the grammar is ambiguous, another parse tree can be like this also. E star E, okay, and this goes to E plus E, and this goes to ID, ID and ID. But we have not constructed this parse tree. We have constructed this parse tree because we already know star is having more precedence. Because what does this mean? This means that plus will be solved first, and then we will multiply. Okay, you already remember all these things from my previous lectures of disambiguity rules. And here the star is having more precedence than plus. That means see, to evaluate this E, we have to evaluate this E as well as this E. To evaluate this E, we have to evaluate both these. So that means what? Multiplication will be done first, na? And this is correct. Obviously this is wrong. This is wrong and this is correct, and by default we have got this parse tree only. Okay, so that is the beauty of this algorithm. So the main advantage of operator precedence parser is this only. We can parse few ambiguous grammars also. Grammar was ambiguous, but still we are able to construct parse tree for a string, and that too in a correct manner. Okay, so I hope I have made the point clear to all of you. Okay, please note it down carefully. I have put everything on the one slide. Okay, then I will jump to the next question. Okay, yes, please try to follow it. Yeah. So for this question, okay, let me give you a let me show you. You can say a string. Okay, so the string is ID star ID plus ID and dollar. Okay, like this. This is our string. Look ahead pointer is pointing to the first symbol. Okay, and now what we will say. Okay, so dollar will be at the end. ID and dollar are compared. ID and dollar are compared. ID is having more precedence, so ID will be pushed onto the stack. ID will be pushed onto the stack. Look ahead pointer will point to the next symbol. Star and ID. Star and ID, we already know that star is having less precedence than ID. Then ID will be popped off. ID popped off means what? ID popped off means what? It will be reduced. Okay, we can imagine that it is reduced. ID is reduced to what? G. Okay, yeah. So next, ID is popped off. Okay, now star and dollar are compared. Star will be pushed onto the stack because star is having more precedence. Then what we will do? Look ahead pointer will point to the next symbol. ID and star are compared. ID will be pushed onto the stack. Okay, now ID will be pushed onto the stack, and then we will move to the next symbol, that is plus. Plus and ID are compared, so obviously ID is having more precedence than plus now. Then ID will be popped off. ID will be popped off means what? This is reduced to G. Okay, now what we will do? Okay, so star plus and star are compared now. Okay, plus is having see here carefully, plus is having more precedence than star. Okay, and forget about it, just check this table. Okay, plus is having more precedence. See the previous slide, but I have told you this part is the stack, and see this row, this entire row represents the buffer, and this column represents the stack. Okay, so this is the stack, and this is the buffer. Okay, now see from the buffer itself. See, in the plus we have read from the buffer, plus we have read from the buffer, and star we have read from the stack. Which is having more precedence? Plus is having more precedence. And why plus is having more precedence? Because this grammar was ambiguous, and according to that grammar we have designed this table. So plus is having more precedence, so plus will be pushed onto the stack. That is very important point. Many students get confused here. They will say plus is having less precedence than star, so plus will be popped off. No. Sorry, star will be popped off. No, plus is having. See, when I used to teach in offline classes, student used to say plus is having less precedence than star. Plus is having less precedence than star, so star will be popped off. No, that is not the case here. Okay, I have already told you. Yeah, now plus is pushed onto the stack. Okay, then look at pointer will point to the next symbol, ID. ID and plus are compared. Obviously, ID is having more precedence, so ID will be pushed onto the stack. Then we will jump to this. We will look at pointer will point to the next symbol, that is dollar. Dollar obviously is having least precedence, so by one will be pop off. So ID will be pop off. First ID will be pop off. ID pop off means what? ID will so from ID will be reduced to G. Okay, then plus is pop off. Plus pop off means what? Plus pop off means, see here, plus means T plus F na. So we will try to make it like this. Okay, so G will become this F. Okay, so and okay, and then this ID, sorry, and then this G. Okay, we want what? T plus F, na? We want T plus F. So F and this F will go to T and this G will go to F. So we have got T plus F and this T plus F will go to what? T. Okay. So this T plus F will go to T. Okay. Now next is C. See the next part. Okay. So then dollar and star are compared. So obviously star will be pop off. Star pop off means what? E star T to E. We want to construct it. E star T to E. Okay. So G. So first we should get here E na. So G will be reduced to F. F will be reduced to T. T will be reduced to E. Now I will say E star T. Okay. See here carefully. Now I will say E star T to E. Okay. And then I will say dollar and dollar are compared. So accepted. String is accepted. Okay. Yes. So this is the case. Okay. And see here in the table I've said dollar and dollar cannot be compared. So it is see when we are finishing the algorithm na, then we will say dollar and this dollar, these are compared. So obviously string is accepted. Like this we have to say. Okay. Yeah. So I think I have made the point clear to all of you. So finally what we have got here, start symbol E. So this is the case. Okay. So see, we are doing bottom up parsers na, and bottom up parsers aim was what? From string we try to generate the start symbol, and here this is exactly what we are doing. From string we are trying to generate the start symbol. See the previous slide also. From the string we have directly generate the start symbol. Okay, that is the beauty of your operator precedence parser. Okay, that is the bottom up parser. Bottom up parser means what? From the string we are trying to generate the start symbol. Okay. Yes. So the algorithm, I think now it is very obvious to everybody. Okay, so you just have to remember these lines which I have given you. More precedence means push and less precedence means pop. That's it. Okay, and this is your stack part, this is your buffer part. That's it. Okay, so these are the few important points which we should remember. Okay, so that's it. So here we have done our operator precedence parser. Okay, so anyhow, you so the important question for this parser is what exactly is operator grammar? This type of question has been asked in GATE exam many times. What are the operator grammar? So I have given you the two rules which we have to remember. And this kind of question has been asked many times in GATE. Which of the following is operator grammar and so on? You have got the more you have got crystal clarity now. Okay, and how to construct the parsing table. Sometimes they may give fill in the blanks here. Okay, so these four may be fill in the blanks for you, that what will be the symbol here and so on. Okay, so I hope I have made the point clear to everybody. Okay, and number of cells in the table and so on. These are the few important questions which can be asked in GATE exam regarding this topic. Okay, yeah. So that's it. So now we are going to start the next parser, that is LR parsers. Okay. Now we are going to start LR parsers. So LR parsers broadly are of four types. First is LR0, second is SLR1, third is LALR1, and fourth is CLR1. LR parser are of four types. And while discussing the parsers, I have already told you that this is the least powerful and this is the most powerful. So according to the power, we can write these parsers. Okay, so I have written according to power only. Okay, increasing order of power only. According to power, this is the least powerful and this is the most powerful LR parser. Okay. So actually all these parsers are almost similar. The basic difference is in the table construction only. That means all these four parsers, or all of these parsers all of these parsers have have similar parts. Okay, similar 4 parts. What are the 4 parts? I have already told you: table, algorithm, stack, buffer. Okay, rather, okay, so these 3 parts are exactly same exactly. The only difference is in table. Table is different for all these parsers. Okay? So table is different. These 3 parts are exactly same. Okay, these 3 parts are exactly same. Difference is in table only. Okay, so let me show you something. Okay, so please note it down carefully. I will jump to the next slide and I will show you some more idea. Okay, so okay, so let me tell you here only. LR0 and SLR1 parser, we need canonical collection of LR0 items. Don't worry, we will tell you everything about it. Canonical collection of LR0 items. For these two, we need canonical collection of LR1 items. So here we need LR0 item. Here we need LR1 items. Okay. So what are LR0 item? First of all, we should know what is LR0 item. Then we should know what is canonical collection of LR0 item. Okay. So let me jump to the next slide and I will show you all these things. Okay. Please note it down carefully. And I'm jumping to next slide now. Okay. So LR0 item. LR0 item. What is LR0 item? LR0 item is production, any production rule of the grammar. Production rule of grammar. Production rule of grammar with dot in the RHS. With dot in RHS. So for example, I can have production rule like this. S implies AA. Now this is not LR0 item because dot is not present. So I can apply dot here. This is LR0 item. This is also LR0 item. This is also LR0 item. Okay. Now see the see this is all LR0 item. No doubt I will say this is LR0 item. But here dot is in extreme right. So this is a special type of LR0 item which is known as final item. Final item means we have, see, dot means what exactly we have read. Dot is it at the beginning, that means we have nothing. Parser has read nothing. Dot is in middle, that means what this A has been read, but this A has not been read. So dot is in extreme right, that means what both A have been read. If both A have been read by parser, then obviously it can be reduced to S now, or it can be reduced to LSS. So this is known as final item. Okay. So when dot is in extreme right, then it is known as final item. Okay. So final item means dot in extreme right. Dot in extreme right. Okay. So I hope I have made the point clear. What are LR0 item? Now I will show you what are canonical collection of LR0 item. Okay. I will jump to the next slide. Please note it down carefully. Yeah. So now I'm going to explain you what is canonical collection of LR0 items. Okay. Yeah. So what are canonical collection? For that, let me take a grammar. S goes to A goes to AA or B. Okay. Now, if I say this is LR0 item, 100% this is LR0 item because I have taken any production rule of the grammar and I have applied dots somewhere. So I can apply dot here, here, here. I can apply anywhere. So I have applied here. Now this is LR0 item, but it is not canonical collection of LR0 item. Why? Because dot is present in beginning of A. So you have to add all the productions of A with dot in the beginning. Okay, then it will become canonical collection. So what I will say, I have S implies A dot A. So I will say dot is present in beginning of A. So add all productions with A in the LHS or having A. Okay, all the productions having A. So with dot in the beginning. Okay, so productions of A are A goes to A goes to B. See here carefully. So I have written it with dot in the beginning. Okay, so I will apply dot here and dot here. Now this is canonical collection. Okay, now this is canonical collection of LR0 item. Let me show you another example. If I say dot, or let me take this dot A. Sorry, according to grammar we will take this. Is this canonical collection of LR0 item? Yes, 100% it is canonical collection of LR0 item. Why? Dot is present in beginning of small a. Now from small a we cannot have any production because this is terminal. So this is canonical collection of LR0 item. What about this scenario? Yes, this is canonical collection, and in fact it is final item also, because dot is in extreme right. A goes to dot B. This is canonical collection of LR0 item, no problem. Okay, and if I say like this, S, or you can say A goes to A dot A. Is this canonical collection? No, this is LR0 item for sure, but it is not canonical collection. Why? Because dot is present in the beginning of A. So we have to add all the productions of A. So what are all the productions of A? A goes to A goes to B. From the grammar, I am saying it. Okay, with dot in the beginning. So you have to apply dot in the beginning also, like this, like this. That's it. Okay. So since dot is present in beginning of A, so add all productions of A with dot in the beginning. That is the basic meaning of canonical collection. Okay. Yes, please note it down carefully, and I will jump to the next slide now. Okay. Yes. So now we will try to construct LR0 parser for the grammar. Okay, so the question is construct LR0 parser for the grammar S goes to A goes to A or B. Okay, this is my grammar, and for this grammar you want to construct LR0 parser. See, the least powerful or the first parser which we are going to study is LR0. Then we will jump to SLR1, then LLR1, and then CLR1. Okay, so in sequence we are going to study. So construct LR0 parser for this grammar. So how to construct it? Okay, so see, actually I think almost 1 hour is over. Okay, so we should study this in the next class. Okay, because in the next class we will make a proper flow of this question. Okay, and I will try to construct this entire parser in one class. Actually the question is very big. If I start this question in today's class, then obviously I have to stop in between, and I have to resume that in the next class. So that will create some mess in your mind. So the better idea is, without any kind of confusion, without any dilemma, we should do this in the next class. Okay, that will be much beneficial for all of us. Okay, in proper flow, I will explain each and everything. Okay, so how to construct the table, how to construct the algorithm, and so on. Each and everything I will explain properly in the next class. Okay, that is a much better idea. Okay, okay then. Thank you so much. Bye bye.